Welcome back, and here we go again, and we are in the middle of discussing bonding. And last time we completed our discussion over ionic bonding. And ionic bonding, we said that I have a metal that loses an electron to become a cation, and then a nonmetal gains an electron, or more than one sometimes, to become an anion, and then the positive cation and the negative anion are attracted to each other because negatives are attracted to positives, and then they form a lattice, and that is what we call an ionic bond and an ionic compound. Now today we went ahead in a different direction. Excuse me. Consider the molecule H2O. Describe the process by which it forms. Okay, so we want to come back. We're going to need to add some notes so we can figure out where to go. Oh my goodness, look at this. I guess this is where we need to be. Okay, so we have types of bonding, right? And we talked about ionic. And now we're going to talk a little bit about covalent. And just to remind each other, remind ourselves, what is covalent bonding? It's bonding in which nonmetals share electrons and form a molecule. Good. So let's go back to our question. Consider the molecule. Describe the process through which it forms. Okay, if we see the word molecule, what are we thinking? It must be covalent. What else would give us an indication it's covalent? Well, we have hydrogen and oxygen. These are both non-metals. So, okay, if it's covalent, and that's probably what it is. And what happens with nonmetals? Nonmetals do what? They share electrons. And what do they try to do by sharing electrons? They share electrons and try to get what? A noble gas electron configuration. Okay, so let's just look at my orbital notation for hydrogen. We've got two of those. And oxygen. Okay, we'll put oxygen down here. Okay, hydrogen is what? I go and I look at my periodic table for hydrogen, and hydrogen has one valence electron. Here's my hydrogen, right? One valence electron. Where's my oxygen? Oxygen is here. How many valence electrons? 6. So we have 1 and 6. Let's come back. Yoink! So I have 1s, 1 electron. 1s, 1 electron. I have how many electrons for oxygen? 8 total. So we go what? 1s, 2, 2s, 2, 1, 2, 3. My 2p, 1, 2, 3, 4. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, right? 1, 1, and 8. Good. Now we said what's going to happen? They both want to get noble gas configurations. Well, let's look at hydrogen. What noble gas configuration can it get? Well, it has 1 electron, and what's its closest noble gas? Helium, and helium has 2. So for hydrogen to become a noble gas configuration, it needs to somehow pick up 1 electron, somehow. And how does oxygen become a noble gas? Well, it could lose 1, 2, 3, 4, 5, 6 electrons, or somehow it could move up to neon by picking up 2 electrons. Okay, so we kind of have an idea of where we're going. Hydrogen wants to get an electron here, and this hydrogen wants to get an electron here, and then this oxygen wants to get electrons here. But how can they do it? If I transfer this electron and it comes over here, then the hydrogen has no electrons. So it can't transfer. And if I go in the reverse, if I transfer this electron here and this one here, well, then my oxygen ends up with what? 1s2, 2s2, 2p2. Well, that's not a noble gas configuration. So transferring is not going to work in this case. So what do you think we're going to do? Well, we say what? We are going to share electrons. So let me beautify this here. I have a 1 electron here. And here, I'm going to move this. So, oh yeah, this is going to be cool, right? Yeah, everything's cool in chemistry. Good. Here we go. Here we go. Yoink, yoink. I'm going to put 1 hydrogen here. And I'm going to say, hey, it has a 1s. So here's my 1s, and there's an electron. And I'm going to put my other hydrogen here, and it has a 1s. Here it is. Good. Now what happens? Well, if I can get this hydrogen orbital to overlap this oxygen orbital, and they share electrons, all of a sudden, how many electrons does this hydrogen see? Well, it sees this electron here, and it sees this electron here. So it feels it has 2 electrons, and that makes it like helium. And if these 2 orbitals overlap, then this hydrogen sees this electron and this electron, so it feels 2 electrons, and it has a helium noble gas configuration. What about the oxygen? Well, this 2p orbital right here sees this electron and this electron because this s is overlapping this 2p orbital. This s is overlapping this other 2p orbital. So the oxygen down here feels 2 electrons here and 2 here. And so what does it have then? 2, 4, 6, 8, 10 electrons, which is just like neon. So by overlapping, by sharing electrons, both hydrogen and helium get noble gas configurations. Neon for oxygen, helium for hydrogen. So that is the process through which water forms. Moving on. Okay, describe the bonding at each of these. Okay, now to describe the bonding, we kind of have to look for a second. Okay, let's do the same way. Let's take the same approach. Hydrogen, we have 2 hydrogens. We'll start in reverse here. 1s, 1s, right? Oops, I need more space. Can't do it that way. Yoink. Hydrogen, 1, oh boy. Hydrogen, 1s, electron. Hydrogen, 1s, electron. Good. So what's going to happen? These 2 orbitals are going to overlap, and each of the hydrogens will now see 2 electrons. And so this would feel like 2 electrons. This feels 2 electrons, meaning they both have helium electron configurations, and this would be 1 bond. Let's think about oxygen. Here's oxygen. Oxygen. 1s, 2. 2s2. 2p4, right? 2p4. Here's a 2p. 1, 2, 3. Hunt's rule, right? 1, 2, 3. Good. Now, what has to happen here in oxygen? Well, we're going to have these guys overlap. And now, does every orbital feel 2 electrons? No, look at these guys are empty here. That's empty and that's empty. So what has to happen? There has to be another overlap here. And so what do we call it if we have 2 overlaps between 2 atoms? Well, this is a bond, and this is a bond. And so what do we call this? If I have 2 bonds between 2 atoms, we call that a what? A double bond. And we would represent that as 2 lines. Each line represents a bond, and each line represents 2 electrons being shared. And we put these between the atoms to represent that they're shared by both. From a hydrogen, we'd have what? It looks like this. 1 electron, each 1 electron here, 1 electron here. It's between the 2, and so sometimes we will make it simpler and just go like that. Good? And of course, we'd have some other electrons on the oxygen, but we're just showing right now the bonding here. So we just kind of say, hey, there we go. That's oxygen. And this is my double bond. And how many electrons are shared there? 4 electrons are shared because each line equals 2 dots, 2 electrons. So if I have double lines, then I'd have 4 electrons being shared. Good. And then let's take a look at nitrogen. Oops, nitrogen. If I look at nitrogen, what is nitrogen? Ooh, beautiful blue there, right? 1s, 2, 2s, 2, and then 1, 2, 3, 2p3, oink, oink, oink. And then same thing with another nitrogen, 1s, no, 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 no. There we go. So what happens? Well, we get an overlap here between these p orbitals, but I still have some places where I need more electrons, so we have another overlap here and another overlap here. Good, so then I have three areas where I have overlapping orbitals, so that means what? This is a triple bond. Triple bond. Good, and so I'd have a nitrogen, and it'd be 1, 2, 3, 4, 5, 6 electrons between the two, or how do we represent that? Yoink, yoink, yoink. There we go, and that represents a triple bond. And if it's a triple bond, how many electrons are shared? 6 electrons are shared. And that is the way nitrogen, each nitrogen gets a noble gas configuration. Now, when I write this, remember, I'm not saying that nitrogen becomes neon, because what makes nitrogen nitrogen? Well, 7 protons, right? Did I change my protons? No. What am I doing? I'm playing around with my valence electrons by sharing or transferring. And this neon only means that they have a neon core now for their electron configuration. Great. Yahoo. Okay, here we go. You guys figure this one out. Pause me, and when you have an answer, come back. Well, this is a piece of cake, right? How many electrons are shared in each bond? Well, that line means what? 2 electrons are shared. There's a double line here. That means what? 4 electrons are shared. And a triple line, that means what? 6 electrons are shared. So this is a single bond. This is a double bond. And this is a triple bond. Yoo-hoo! Great. Let's see how we're doing on time. Oh, wunderbar. I think we can go a little farther. What do you say? Okay, consider the molecule carbon tetrachloride. Draw the Lewis structure for this molecule. Ach du Liebe. What are we going to do here? Well, we have an idea. We have a molecule, and we have some stuff here. It says draw the Lewis structure for the molecule. Well, we're going to need some rules here, so let's write down some rules. We want to draw Lewis structures. Oops. Lewis structures for molecules. For molecules. And there are a set of rules. Rule number 1. Now, you remember what Lewis structures are, right? It is something where it's a diagram where I show my valence electrons. Rule number 1, here's the way we start. And I recommend that you follow this rule and don't guess. And also, I recommend that you use pencil because you're going to have to erase at times. Number 1, count valence electrons in molecule. Okay. Whoops, molecule. Good. How do we do that? We use our periodic table. Oink. Okay, what did we have? We had carbon and we had chlorine, right? I had 1 carbon and I have 4 chlorines, right? Now, valence electrons, 1, 2, 3, 4, 5, 6, 7. So carbon has 4 valence electrons, and chlorine has 4, 5, 6, 7. Chlorine has 7. That's not a 7, that's a 4. And how many chlorines do I have? I have 4 chlorines. So that means I have a total from the chlorines of 28 valence electrons. Okay, so I have 28 valence electrons from chlorine, 4 from carbon. Good. Count the number of valence electrons. So we'd say we have, what, 28 and 4, 32 valence electrons. Number 2. Let's go back to black. Number 2. Choose a central atom for your drawing. Choose central atom for drawing. Okay, good. So what am I going to choose? How do I know? Here are some hints. Think symmetry. Symmetric. Choose a central atom that will make things symmetric. Okay, another hint. Never hydrogen. Another hint. Many times, often. carbon, and here's another hint. Quite often, it is the least, it's the atom with the least electronegativity, meaning farthest from fluorine, right? And finally, um, take hint, that's stupid to say it that way. Often, um, often the formula often shows bonding order of bonding. And what I mean by that, if we have HCN, they're telling me that the H is bonded to the C and the N is bonded to the C. So when you see that order, right away they're telling me, hey, my carbon here is probably my central atom. So this is kind of the rule of thumb. What are we dealing with here? We're dealing with carbon tetrachloride. Well, I have one carbon and 4 chlorine, so that would indicate that carbon is my, if I put carbon in the central, then I would get a symmetric arrangement. Not only that, we say quite often it is carbon. So let's put down this. I'm going to put carbon in the center, and we're going to surround it with chlorines. Okay. Then what am I going to do? Number 3. 3, we want to bond atoms to central atom. Remember, that line means 2 electrons, right? So let's put a bond here, let's put a bond here, let's put a bond here, and a bond there. Great. Now, for complete octet. Remember our octets? We said, hey, we're going to assume most atoms want to have 8 valence electrons when bonded. Okay, so that means we want to make sure each atom has 8 valence electrons. And remember, this line means there are 2, right? That's 2 electrons. So 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. How many are on my carbon? 2. Oops, can't put a dot there. Yoink. That line is 2, this line is 2, this line is 2, and that line is 2. So my carbon has 8. So my chlorines and all my carbons have 8. Good. 5. Add some, I should say, some the electrons in drawing. Good. If same as number of valence electrons, then you're done. Okay, let's see if we're lucky. All right, let's go up here. How many electrons do I have? I'm going to do this with a red. So if you see a red dot, that doesn't mean I'm really adding dots, but I'm counting. I'll do checks. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we have 32 electrons in the drawing. Now, how many valence electrons were we allowed to put in the drawing? We said what? 32 valence electrons. Woohoo! 32 and 32, they equal each other. Well, that is exactly what's supposed to happen. Good. So my drawing has exactly the number of electrons as my valence electrons. All my atoms have 8 electrons. They have their octet, and that means they all have what? They all have noble gas configurations, and that would be a good Lewis structure. All right, let's see if you can do one. Here we go. You guys do carbon tetrafluoride, and then we'll call timeout for the day. All right, what did you do with carbon tetrafluoride? What's the first thing we do? Count valence electrons. Well, we know carbon has 4. Let's go up to fluorine on our periodic table. For its fluorine, here is fluorine. How many valence electrons? 4. So this is 4, and how many of those, not 4, 7. Sorry, I just can't read. I have 4 times 7, so that means I have 32 valence electrons from fluorine. I have 4 from carbon. I add those up. No, I can't. That's wrong. 4 times 7 is what? 28. Yahoo! I can't add. So 4 plus 28 is 32 valence electrons. So that's how many I need to show in my drawing. Good. Now what do? We want to choose a central atom. Well, do I want to have fluorine? I have 4 fluorines, and I have carbon. Which one would give me a symmetric arrangement? I think carbon. So I'm going to put my carbon in the middle, surround it with my fluorines. Then what? I'm going to bond my fluorines to my carbon, and then I need to make sure everything has 8 electrons. All right, carbon. 2, 4, 6, 8. My carbon's fine. How many does my fluorine have? Well, it only has 2, so that's 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Wow, just like doing push-ups. Good. So now all my atoms have an octet. Now we need to add, we need to count all of these, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Woohoo! So I have 32 electrons in my picture. How many were available? 32. And so what should this look like? Let's clean this up. It should look like this, right? This would be my completed, oops, not hydrogen, yoink, F. And then 2 electrons around each side. And that is my excellent Lewis structure for carbon tetrafluoride, showing all my valence electrons and how every atom has an octet. All right, I think that'll do it for now. Next time, we'll get into some exceptions. Ciao, Bella.